Hey there! In this video we are looking at applications of exponential functions in real-world situations that involve growth and decay. This is part one, where the problems we're going to look at involve a period of 1. Or in other words, the rate of change is being applied every 1 unit of time. So we could have something that's growing by 20% every year, or it's doubling every month, or it's getting cut in half every day, or something like that. All right, we're going to look at two different examples of applications of exponential functions here in part one, where the period is 1. The first one of those is a situation involving exponential growth, and the second one involving exponential decay or decrease. Here we have a student who's investing $1,000 in something that pays her 10% interest per year. And the important part here, which makes it exponential, is the fact that it is compounded annually. Now what that means is every year she gets paid 10% of the value for that year, not 10% of the initial amount every year, 10% of the value. So we're going to complete this table down here and we can see what's happening a little more clearly. At the beginning, times 0, she has $1,000. After 1 year, she is going to get 10% of that as interest. So 10% of 1,000 is 100, so she's going to have $1,100. Now, the key here is that after 2 years, she isn't going to just get another $100, 10% of the initial amount. She gets 10% of this amount, the value after the first year. So she's going to get $110. So she doesn't just have $1,200, she has $1,210. That extra $10 is interest from the first year, interest on that $100 that she got in the first year. And then in the third year, she's going to get 10% of this amount here, which is $121. So she's going to have a total of $1,331. So she's not getting the same amount every year. And we could keep going with the table to the right here and determine more years for this. But we're going to try and generalize this here, and so that we can use the concept to solve some problems without having to go through every year one at a time. If you think about it, every year she has 110% of what she had the year before. So this amount is 110% of this amount. And this amount is 110% of this amount, and so on. If you want to think about it visually here, you can imagine that the initial amount, your 100%, whatever that happens to be every year, you tack on the extra 10% every year. So in total, after every year, you have 110% together of what you had the year before. So how you can think about that then is, you can take this amount right here in any given year and multiply it by 110%, or in other words, as a decimal, 1.10. And then the following year, you can just do the same thing again, multiply it by 110% again to get the next value, and again to get the next value. So really what you're doing is repeatedly multiplying by 110%. And in fact, if you want to get, say, this third year expression and amount, you can get it directly from the start amount by recognizing that you've multiplied 3 times by 110%. So you can write an expression for that third year amount by thinking of it as $1,000 times 110% to the power of 3, 1.10 to the power of 3. This expression will directly give you that amount from the start without finding those ones in between. And so what we can do here is we can write a general function for the value in any year that looks like that, right? Just recognizing that you are multiplying by 110% repeatedly. So your value at any time, where x is the time in years, that exponent up there, if we put a number in there, so for the third year up here, we use a 3, and then y I'm using as the amount after that many years. This is a function you can use to represent the value of the investment at any time after any number of years. And we can use this function to determine unknown values and solve some problems. First of all, what we're going to find is we're going to look for the value of the investment, or in other words, the accumulated amount in the account after a given amount of time here. So what we're looking for in our function is we're wanting to know what's the y value for a given x value here. So we can determine y when x is 8. So if we write our function but then substitute in 8 for x for the time in the exponent, and then go to the calculator to work that out. I won't actually go to the calculator right now. I'm sure you know how to punch that in and determine it. The only thing to make sure you do is make sure you work this out before you multiply by 1,000. Don't multiply these two first and then raise the whole thing to the 8th. The 8th power only applies to that part of it, but you do it, you should get $2,143.59. Now, before we move on to something else, we're going to check our answer graphically here. And to do that, we're going to graph our function, y equals 1,000 times 1.10 to the x, and graph it together with the line x equals 8 and look for the intersection. Now, in lots of my other videos, I've graphed functions and verified things graphically, so I'm not going to actually go and do that right now, but you could on Desmos or GeoGebra on a graphing calculator create that graph, and what you'd find is it looks something like that. You have this, what is hopefully familiar to you, that exponential graph, that curve, along with the line, x equals 8, that vertical line, and that intersection point right there has the coordinates 8, of course, and the y coordinate is our solution. So it's a graphical way of finding that y value, and it matches up with the value we found algebraically. The last part of our first situation here is we're going to look for how long it's going to take before the value of her investment becomes $3,000 if she can leave it invested for a long time. And we're looking for a time in this case, so kind of the reverse of what we just did before. We're looking for the x value when we're given the y value. So what we're going to do is we're going to try and solve for x when y is a given value of 3,000. We're going to take our function and then replace the y with 3,000. It creates an equation. It's an exponential equation because the variable is in the exponent. For this particular equation, I think the best first step here is to divide both sides by 1,000 because we can get rid of this 1,000 on this side, and we end up with 3 on the left and 1.10 to the x on the right. Now, that simpler equation, we can solve it by taking the logarithm of both sides, and that allows us to use the power rule for logarithms and put that x in front, so we end up with that. Log base 3 equals x times log base 1.10, and now it's just x times this number, log 1.10. So to solve that, we can divide both sides by log 1.10, and that's going to leave us with the value of x being log 3 divided by log 1.10, and if you go to your calculator and do that, you're going to find that it's approximately 11.5. So then the solution to our problem here is approximately 11.5 years it's going to take before the value is that. Now you might say, well, she doesn't get paid the interest till the end of the year, so maybe we should say 12 years, but we're not going to worry about that in this case here. Now it's probably worth noting here that you could actually solve this a slightly different way. When you get to that step in the solution, we used base 10 logarithms of both sides, common logarithms, because that's what most calculators have. If you happen to have a calculator that has some kind of log base or other equivalent feature, you could take the log base 110 of both sides, and what you would end up with is you'd end up with that. If you take the log base 1.10 both sides, then it's going to just directly cancel it out on this side, and you end up with x being equal to log base 1.10 of 3, and you can put that into your calculator. You're still going to get 11.5 when you do that. That's less common. Most calculators don't have that log base thing on there because you can always just use base 10 logarithms. Now, before we finish this, we're going to go back and do the same thing as we did before, which is check our answer graphically. To do that, we're going to do something similar to what we did before. We're going to look for the intersection point between our function, right there, and this line, but the line is going to be y equals 3,000 this time. Again, you can go and create that graph on your graphing app of choice. When you create the graph, it's going to look something like that. This time y equals 3,000. It's a horizontal line because we're given the y value and we're using it to find that x value. And when you do that, the x coordinate, 11.5267, that matches up with what we found. All right? Our second example is one involving exponential decay, or in other words, a value that is decreasing exponentially. Here we have the population of a school that is currently 1,250 students, and it is decreasing at an annual rate of 3%. Now, we could approach this the way we started with the first example, as in working out what 3% is, and then subtracting it from this value, because it's decreasing, and then getting our value after 1 year, and then working out what 3% of that value is and subtracting it and going 1 year at a time. But we're going to use some of what we learned in the first example to expedite the process here a little bit. First of all, what we need to recognize is that if 3% are leaving every year, that means that 97% are staying every year, or in other words, 100% minus 3%. If we look at it visually like we did in the first one, imagine you have your 100% here. That's the value in any given year. In the first example, we tacked on 10% on the top. Here, if we take off some off the top, 3%, then what we have left is 97% every year. All right, so each year the school has a population that is 97% of what it was the previous year. So to fill out this table, we can use that idea to make it a lot more efficient. So we start at year 0 with our 1,250. So if each year the school has 97% of what it had the previous year, we can take that value of 1,250 and multiply it by 0.97. And so we get after 1 year that we have 1,213. That's rounded to the nearest whole number because we're talking about students here. After 2 years, we can do the same thing again. Multiply by 0.97 again. And if you go to your calculator and check, you'll get that much. And again, after 3 years, multiply by 0.97 again, and you'll get that value, 1141. Now, just like in the first example, we can write an expression for this value directly from the initial value based on the number of years, just by recognizing you're repeatedly multiplying by 0.97. So an expression for that would be our initial value of 1250 times 0.97 after 3 years to the power of 3, because you've multiplied it by 0.97 3 times. And then what we can do is write a general function that we can use. And our general function is going to look like this, except a variable in there. So it looks like that. I'm using P for school population and T for time in years in this function. Now, like before, we can use that function to solve problems and find some missing values. First, what we're going to do is we're going to work out what the school population is 5 years from now. So what that means is we can substitute T equal 5 into our function and then evaluate it to find what the value of P is. So if you write your function there, with the 5 substituted in for time, and put that in a calculator, again, evaluating it properly, you get that the school population is approximately 1,073. Again, I rounded it to the nearest whole number because we're talking about people here. You could also check your answer graphically as before, graph that function with the function t equals 5. Now I'm using p and t here. You could use x and y, and in fact, on most graphing apps or programs, you're going to have to use x here and y here, and then this would, of course, be x equals 5. And when you do that, you'll find that you get a graph that looks something like that, and so you're going to get that, hopefully, again, familiar exponential curve going down because you have this value, the rate, the base there is less than 1, so the curve is going down, which makes sense when it's decreasing. And then you find that when you find the intersection point with the vertical line 5 there, you get 1073. All right. The last part of our second example here is we're looking for when the population of the school will drop down to 900 students. And like in our first example, the last part was kind of a reverse here because we're looking for time here given a value of number of students. So we can substitute 900 in for p and then solve for t in our function. Our function looks like that when you have the population replaced with 900. Again, I've been using p and t the whole way down, but if that is something you don't like, again, you're welcome to use y and x throughout. I think, again, the best first step here is to divide both sides by 1250 so that this can cancel out and we simplify things a little bit here. And we end up with, on the left, 900 divided by 1250. And on the right, we just have 0.97 to the power of t. What you can do from there is take the logarithm of both sides. And when you take the logarithm of both sides, it lets you take your variable and put it in front there. So that what you have on the right is t times log 0.97. On the left, you have log of 900 over 1250. And from there, you can keep isolating the t by dividing both sides by log 0.97. And so on the right, what you have left is just a t, and on the left, you have log 900 over 1250 divided by log 0.97. Depending on your calculator, you may have to put brackets around this. You may have to put brackets around every number. Just be careful with it. But if you've done it successfully, you will get 10.785 approximately, or we can say approximately 10.8 years. Now, again, you might argue that, well, since the school population probably doesn't change much throughout the year and changes from year to year, maybe we should answer 11 years, but we're not going to worry about that. And we should point out as well, again, that just like the first example, instead of using common base 10 logarithms here, we could use base 0.97 logarithms on both sides at that stage and solve it that way. If you want to do that, that is up to you. All right? Now, before we're done here, it's probably worth just generalizing the model function we used in both examples, because that's the key to being able to solve all of the different parts of the problems that we did. In both cases, we used a function that looks something like that. Now, I didn't use all of those variables in both of them, but if we think about the two functions we did use, the one we just used here was p equals 1250 times 0.97 to the t. And in the first case, we used y equals 1000 times 1.10 to the x. Those two look a little bit different, but in both cases, we had some amount after a certain length of time we can find by taking our initial amount and multiplying it by our rate to the power of whatever the length of time was in both cases. In the second case, p was that initial amount times that rate to the power of that time. Whether you use t or x or y or p or whatever, it looks something like this. The amount after a certain length of time t is our initial amount, y0, used to represent initial amount. I'm using r to represent rate and t to represent time here. But you could write a function with whatever variables in each of those positions that you want. So just to make sure it's clear for each of those variables, y0 is our initial amount, r is our rate, t is our time, and y is our amount after that time, after time t. All right, that's it. For part 1 anyways, where the period is 1, I suggest you go on to part 2, where the period is something other than 1. What I mean by that is the rate is applied not every year or every week, it's applied every 5 years or 2 weeks or something like that. But again, go on to part 2 to find out more about that.